Namaste. Let us start the last lecture of week 11. In this week, we have started discussing about the various techniques which are routinely used for the characterization of nanomaterials. We have been talking to you about the techniques which are classified under various subheadings, and we have spent significant amount of time on understanding the way we can determine the crystallite size or particle size using X-ray diffraction, and we have also given you the introduction towards the use of SEM and TEM. We will talk in the next week in more detail about the use of SEM and TEM to determine the morphology of nanoparticles. In this week, let us today discuss about another parameter which we had introduced in the initial part of this lecture series. We had talked to you that as you change the shape and the size of the particles, there is another parameter which gets modified, and that is strain. The origin of strain or the modulation of strain directly impacts both physical as well as chemical properties of the materials which are of our interest. So, we should ask the question as to how does the strain in crystals impact the properties of such particles which we are synthesizing. If there is a strain, then do we always have only one type of strain, or there are various types of strain? Once we understand that, we should find out the technique which actually allows us to quantify the magnitude of strain, so that we can contribute the modulation in the physical or chemical properties to the changes in the crystal lattice or the size of the material to the appearance of strain in this configuration which we are investigating. We had seen that even if we consider spherical particles, there also there is a continuously changing strain which is felt on the surface of such particles. So, we should find out the measurement techniques by which we can determine the strain on the bulk particles, and we should also find out what is happening at the micro level, that is at the level of the lattice, and see that if there is strain appearance at the lattice level, then can it impact the behavior at the bulk level. So, we will talk about the strain measurements using the lattice parameter method. We will also talk about the residual strain, and using the Williamson Hall method, we will try to then analyze the mathematical formulation using which we can correlate the microstrain with the crystallite size. And then we will talk about the advantages and certain limitations of using the X-ray diffraction data for such analysis. In today's lecture also, we will use X-ray diffraction data as the model data set. The reason is very simple. In today's experimental physics, X-ray diffraction is one of the most commonly used technique which is readily available in most of the institutes. So, and you will find that such techniques are also based on simple principles which are well understood at your level. We are talking about diffraction and interference, we are talking about superposition of waves, and we are talking about wave particle interaction. These concepts are already well understood by us. So, if we can use these concepts and build certain mathematical models to derive quantities like microstrain, lattice strain or strain at the bulk level, then it would be very easy to understand and explain to the end user the changes in the properties of a device which is being fabricated using such materials. We can then define the operation conditions at which such devices would be useful. For example, if we say that there would be significant change in the lattice parameters if you change temperature, for example, from room temperature to 50 degrees, then there is a lattice strain and overall you start seeing thermal expansion in most of the materials. Please note, I am saying most of the materials because now it is also understood that there are materials which show negative thermal expansion. That means when you heat them, they actually contract, but most of the materials expand when you heat, and when they do, then they introduce strain in the lattice, and because of that there are changes in the physical properties that will decide the application range as well as the operation conditions for such devices which are based on the materials that we are talking about. So, that is very important for the end user, so that the device does not get damaged because of use in conditions which are not favorable for the materials which are used to fabricate such devices. So, strain in a crystallography will refer to what? At the crystallography level I am asking, will refer to relative change in the lattice parameter. Generally we say the change in the size of the overall material, but when you are going at the crystal level, we are talking about the relative change in the lattice level. So, you will have relative change in the lattice parameter compared to what? Compared to a stress free reference. So, mathematically you will be able to write the change is equal to, or strain is delta D by D0, where D0 is the interplanar spacing in the unstrained reference crystal and delta D is the change in spacing due to applied stress, defects, processing conditions or operating conditions. So, you can have strain appearing because of external stresses, thermal mismatch, defects, or dislocations, grain boundary mismatch, ionic substitutions or even doping in such solid materials. So, there are huge number of parameters which will lead to the appearance of strain, and that is why it is very important to understand the concept of strain and what is the magnitude of that in a given material. Else sometimes we are unable to understand the appearance of certain properties or separation of certain properties in materials because of factors which we have not considered. So, even a very small change in the lattice parameters can be detected by X-ray diffraction, because its sensitivity is very high towards changes in the lattice spacings. So, if strain changes the atomic positions, the volume size, the lattice parameters, the broadening, the shape of the profile, all these things can be very critically monitored using X-ray diffraction. So, we have seen that there are various factors which would lead to the appearance of strain, and if there are various factors which would lead to the appearance of strain, that means you would also see that there is a possibility or there are possibilities of various types of strains, and the commonly encountered strains are macro strain or micro strain. The macro strain, which is also classified as uniform strain, is a homogeneous deformation across a crystal or a polycrystalline material. So, this is like a strain felt throughout the system, and it shifts the entire set of diffraction peaks uniformly, because sometimes we can say that if there is a uniform shift in the diffraction peak, then it can be due to the instrumental error which has resulted in the shift in the of the positions. But if our instrumental error is eliminated, then if you have micro strains, in these macro strains you will find that the whole diffraction peaks would be shifting uniformly. These are mostly caused by external stresses such as mechanical load, thermal expansion mismatch, residual stresses which are felt after processing. And for example, the residual tensile stress are routinely felt in the thin films which are grown on substrates, but the substrates have parameters which do not match with those of the films which are grown on it, and then there would be a complete shift so that the mismatch can be minimized. Then you can have the second type of strain, those are called as micro strain, non-uniform strains. These are local variations in the lattice spacing due to defects or dislocations, grain boundaries or local stresses which may appear because you can have coexisting phases in a solid solution. And then because of these competing structural instabilities, you can start seeing local stresses in the lattice, and which induces these kind of micro strains. This results in the peak broadening rather than a uniform peak shifts. These microstrains are basically a representation of inhomogeneous strain field distributed across the crystallites and are routinely encountered in cold work metals, nanocrystalline materials, and if the systems have high defects, then you will find the contribution from microstrains are even higher. X-ray diffraction technique is a commonly used technique for strain measurement. As we have seen, it is a non-destructive method, it is contactless and it is very versatile, and you can actually differentiate between the macro and micro strain, and that is a beautiful advantage of this technique. Along with that, it gives you high resolution and provides statistically reliable strain information, while you can also carry out the studies to capture or analyze strain variations while the system is undergoing certain variations in the condition or operating conditions. For example, if you have a material which is being cooled or is being heated, then is the lattice stable or it is showing some kind of strain appearance. That you can just determine by analyzing the temperature dependent X-ray. You can also apply pressure and that can lead to strain appearance. You can apply stress in the real time and then collect the X-ray diffraction data, analyze it, get the alpha, beta, gamma, ABC parameters, and you can find out the magnitude of strain which is getting stabilized. So, it is a very simple but a powerful technique to carry out the strain analysis. For example, let us have an XRD peak position with a interplanar spacing DHKL. So, now you have Bragg's law. So, you can write lambda is equal to 2D HKL sin theta, and that will give you DHKL is equal to lambda upon 2 sin theta. Compare the measure D to an unstrained lattice. So, you take a condition when the lattice is not strained and you get a parameter A0. So, if you want to determine the magnitude of strain along the x direction, let us say in which you are measuring a lattice parameter A, then epsilon is given by A minus A0 by A0, and that is a straight away determination technique to get information about strain. For example, for cubic crystals, A is equal to DHKL into under root h square plus k square to L square. For non-cubic systems, you can use the appropriate relations to convert DHKL to lattice parameters, and you can then use these values to determine the values of epsilon. If you look into a typical X-ray diffraction pattern, you will find that, let us say you have applied no strain, then the lattice is periodically arranged and a diffraction pattern appears at a given theta or 2 theta. When you apply a uniform strain, then the lattice elongates, the peak shifts, but there is no change in the shape of the peak. But if you have non-uniform strain, then you see that the nature of the lattice is changing due to non-uniform strain, and you get peak broadening along with slight shift in the peak position. So, just by looking at the change in these peak profiles, you can start getting information about the nature of strain, and using the mathematical formulations you can also quantify the strain. Now, if you look into the peak shifts and peak broadening together, you will find that both when brought together will give you the full picture about the strain state and the nature of it. If you have shift towards low theta, then you are talking about tensile strain. If you are seeing higher 2 thetas for a peak profile, then you are talking about compressive strains. Now, let us see, can we get some information about the residual stress. Now, let us say from the Hooke's law, then what do you get? You have the elastic strain epsilon is known, then the residual strain can be estimated using the relation sigma is equal to E into epsilon upon 1 minus nu, where E is the Young's modulus and nu is the Poisson ratio. Now, by this you can get information about residual strain, or you can use sine square psi method. So, now you start tilting the sample at different angles relative to the incident beam and measure the d at each time, and now you can plot d versus sine square psi plot, and the slope is directly related to the residual strain. So, you can easily get the values of residual stress. If you want to now go and determine the micro strain, then the Williamson-Hall method is used, and it considered that there are two effects that results in the broadening of diffraction. You can have finite crystallite size as well as lattice microstrain, and the full peak broadening beta can be written as beta cos theta is equal to k lambda by L plus 4 epsilon sin theta. And from here, by plotting the curve of beta cos theta versus 4 sin theta, the intercept will give you the crystallite size L and the slope will give you the microstrain epsilon. So, it becomes y is equal to mx plus c kind of curve, and therefore, you can get the intercept and the slope, and from there you can straight away get the values of crystallite size as well as the microstrain. So, using FWHM, the fitting parameter given lambda, you can get these values of the unknown. And knowing these values, you can then correlate the behavior to the microstrain related to mechanical behavior of the materials. So, you can just look into the typical curve which you will get. You plot beta cos theta versus sin theta, you get a distribution of points, then you have a linear fit, and then you can determine L and epsilon. So, in this case the crystallite size is approximately 61.5 nanometers and lattice strain is approximately 4.5 into 10 raised to power minus 4. You can also have complex structures, and when you prepare them at different temperatures. So, now you have changed the temperature at which you are preparing these materials. You can see that there are some changes in the peak broadening, and with that you can calculate the change in the strain. So, you take a sample prepared at various temperatures, and you can then use either the Scherrer formula to determine the crystallite size, or you can use the Williamson-Hall method to determine the crystallite size, and along with that you can use the Williamson-Hall method to determine the strain in these materials. So, you can see that synthesis conditions change the strain which are felt by the lattice as well as the crystallite size which are formed in these materials. If you summarize all these things, you can see that X-rays will give you the advantage of characterizing crystalline or polycrystalline materials easily. It is a non-destructive method which can be quickly performed. You can use bulk samples, powder samples, thin films, coatings, and you can perform both ambient and non-ambient condition studies in these X-ray diffractometer based analysis. You can quantify both macro as well as micro strain. You do not need to carry out separate tests. The modern high resolution diffractometers are highly sensitive, and you can achieve strain accuracies of 10 raised to minus 4 or even higher. With microbeams or area detectors, you can also map the strain variation on samples, and that will give you spatial strain maps on the sample, which becomes very useful if you are trying to use certain materials for electronic applications or mechanical devices. But there are limitations, that it is mostly surface sensitive. You need the elastic constants beforehand. Sometimes there is a stress gradient, because X-ray gives you an average over its penetration depth. Therefore, it may miss gradients through the thickness. If you have preferred growth, preferred orientation, or anisotropy in the structure, then it can actually complicate the overall analysis. Hence, there are alternate techniques which are used, or there are techniques which are used to supplement the results obtained using X-ray diffraction studies at the laboratory level, and these techniques are like neutron diffraction or synchrotron high resolution X-ray diffraction studies. So, now we have studied about various characterization techniques, the introduction to them. We now have an understanding how to determine the crystallite size, and we also know how to calculate the strain in these materials, and we had earlier studied that both morphology and strain directly impact the response characteristics of nanomaterials. And now we know a very simple technique which can be used to give information about both these parameters. So, now what you have? You have understanding about nanomaterials. What are those? You can classify nanomaterials into various subclasses. You can use physical models to understand the change in the energy level in these systems. You can understand the effect of quantum confinement. You can also see the band gap modulation in these materials as a function of changing size, which can be modeled using nearly free electron model. You have the knowledge about the synthesis of these materials. We have talked about the application of these materials which depend on various properties of the materials. And now you also have the understanding of few techniques which are actually used to quantify those properties so that they can be utilized in devices. These are some of the references which would be very useful to go through to develop even more understanding about the topics which we covered today, and I thank you for attending the last lecture of week 11, and in the next week we will start our lecture with the introduction to TEM and SEM. Thank you very much.